In this experiment, 4 properties of a lens would be investigated. This includes focal length, aperture, depth of field, and chromatic aberration. These 3 properties work together to form an image. However, chromatic aberration may be characterized as a defect within a lens.
In photography, the focal length is used as a primary descriptor of the lenses. The focal length is used to describe lenses because it shows what the field of the lens would be. Since the sensor remains the same size regardless of the lens, the field of view tells us how much a lens can magnify distant objects. In other words, how zoomed in the pictures can be. The shorter the focal length, the wider the field of view. The longer the focal length, the narrower the field of view. It measures the distance between the rear nodal point and the focal point of the lens while the lens is focused to infinity. The purpose of a photographic lens is to take parallel rays of light and converge them into a single point of focus to be recorded, either on a piece of film or a digital sensor rather. The point at which the lens caused the light rays to converge is called the focal point. Since in photography there are multiple lenses, these lenses work together to converge light with as few optical aberrations as possible. There is therefore no center point, the reason for measuring the focal point from the rear nodal point. The focal length of a photographic lens is generally between 14 mm and 600 mm. The human eye has a focal length between 40 mm and 58 mm. This focal length is known as the normal focal length. Any lens with a focal length shorter than this is a wide-angle lens, and things in this image would appear smaller than they look to the natural eye. Any lens with a focal length longer than the normal focal length is known as a telephoto lens, and things in this image would appear larger.
Aperture is the opening through which light travels. The aperture and focal length determines the angle in which rays come into focus on an image plane. When the shutter release button is hit, this allows the opening of the camera to catch a glimpse of the desired image. The f number of an optical system is the ratio of the system's focal length to the diameter of the entrance pupil. It is a dimensionless number that measures the speed of the lens. Moving from one f-stop to another changes the size of the opening of the lens, which relates to the amount of light that enters the lens. If compared to the human eye, both aperture and focal length work together to translate an image upon the retina. The pupil of the eye can be seen as large as 6 to 7 mm wide, which is the maximum physical aperture. The f number of the eye varies from the f-stop of 8.3 in brightly lit places to an f-stop of 2.1 in dim places. But theoretically, our actual sight is from a minimum of the f-stop 3.2. So how is aperture even useful? In cameras, the aperture can be quick, precise, and accurate. It is advantageous to people with less than perfect vision sights. Aperture may affect the brightness or exposure, the depth of field, the sharpness due to diffraction, and lens quality, the focus shift, and the ability to focus in dim light as compared to bright light.
When you focus on an object, that object is sharply focused. But what about the object that's, say, an inch behind it? Or even a foot behind it? Depending on your camera settings and lens type, the depth of field may be just millimeters or a few dozen feet. Depth of field is the range of distances that appears in focus. A shallow depth of field is present when only a small portion of the image is sharply focused, while the background is unfocused. A shallow depth of field is used in portraits because that unfocused quality eliminates anything distracting from the background and draws more attention to the subject. However, a narrow depth of field implies that a large portion of the image is sharply focused, even for objects that are a little way from the focal point. Landscape use a narrow depth of field to show more of the scene. The depth of field determines how much of the image is in focus. Factors that affect depth of field are aperture, distance, and focal length. Firstly, aperture refers to the access given to light from the lens to the camera sensors. The size of your aperture, that is, the size of the opening in the lens, controls the amount of light entering your lens. A wide aperture or low f-stop number results in a shallow depth of field. At wide apertures, an object needs to be very close to the original focus point in order to be sharp. That's why in portrait photography, it is important to focus on the eyes. Otherwise, if the focus point is on the nose, the face may not be in focus with such a shallow depth of field. On the other hand, a narrow aperture or a high f-stop number results in a narrow depth of field. Objects don't have to be very close to the original focal point in order to remain sharp. Landscapes tend to use very high f numbers so that almost the entire scene remains sharp. Secondly, the distance with distance. The closer your subject is to the camera, the shallower your depth of field becomes. In essence, moving further away from your subject will deepen your depth of field. Thirdly, focal length refers to the capability of a lens to magnify the image or a distant subject. The longer you set your focal length, the shallower the depth of field. Now we have learned about depth of field and the importance in maintaining and getting and achieving a beautiful scenery and your desired focus on an image. In conclusion, depth of field is a valuable element in understanding how we get sharp and soft images and the resulting backgrounds in the image. A portrait may require a shallow depth of field, while landscapes are best with a narrow depth of field. Depth of field can be adjusted in more ways than one. Aperture plays a role, so does distance and focal length.
Chromatic aberration is an optical problem which happens when a lens is unable to focus all wavelengths of color onto the same focal plane, and it also occurs when the wavelengths of the colors are focused at different points on the focal plane. Chromatic aberration occurs due to lens dispersion of different colors composing of light that travel at different speeds while passing through a lens. This results in the image appearing blurred or with noticeable colored edges appearing around the object. These colored edges show up as red, green, blue, yellow, purple, or magenta. A perfect lens, in theory, is able to focus all wavelengths into a single focal point with the best focus. However, in practical situations, each color has a different wavelength, and in turn, the refractive index for each wavelength is different, thus resulting in two types of chromatic aberration occurring. These include longitudinal chromatic aberration and lateral chromatic aberration. Longitudinal chromatic aberration is due to various wavelengths of colors not converging at the same point in the focal length range after passing through the lens. This can occur with high-quality lenses, and the colors red, green, and yellow are mostly seen. Lenses with this type of chromatic aberration shows objects with fringing around it throughout the image, even at the center. Longitudinal chromatic aberration can be significantly reduced by using slower lenses than fast aperture lenses, which are more prone to longitudinal chromatic aberration. It can also be reduced by post-processing and using a lens correction module. Lateral chromatic aberration, on the other hand, occurs with the different wavelengths of the color at various angles, falling on the same focal plane, within the focal length but at different positions on the plane. This type of chromatic aberration is only visible at the corners of the image in high contrast areas. This occurs with low quality lenses and has blue and purple fringing. This type of chromatic aberration can only be fixed using post-processing software. Chromatic aberration is therefore an artifact which is wavelength dependent and occurs in the human eye when viewing objects. Example, when viewing a purple dot on a paper, As this paper is brought closer to the eye, it appears blue with a red halo. However, the distance is changed and carried further away from the eye. The dot then appears red with a blue halo. This shows how the wavelengths of the colors fall on the focal plane after passing through the lens in the eye, and how changing distance of the objects affects the positions in which the wavelength rays fall. Wavelengths are refracted based on their frequency. When passing through the lens, the refractive index is needed. The refractive index of the color blue is greater since the wavelength is shorter, and as the wavelength is decreased, this changes at a rapid rate. However, with the human eye, this does not show up often because the brain is able to process the images compensating for the chromatic aberration. Chromatic aberration is very popular with single, thin lenses and utilizes the lens maker's formula. The focal length also varies with the wavelength of light as it passes through the lens and demonstrates chromatic aberration through the single, thin lens. Factors that affect the image seen with chromatic aberration occurring are distance of the object from lens, focal length, and aperture of the lens.